Hello developers, let's start developing. My name is Veko and today we're gonna be solving the 16th puzzle for the Advent of Code 2021. I've read through this puzzle and there is quite a lot to read through, so I will give you a quick run through. So we are getting some hexadecimal data as input. This is the data we're getting. And basically what we need to do, we need to somehow decode it. And this data is basically some packages. Actually, this is a single packet, and we are getting a single packet, but one packet can have multiple packets inside of it. And so we have two kinds of packets. We have packets that contain sub-packets and something that is called literal packets or something like that. The type ID. So we have type ID 4, which represents a literal value, and type ID not 4, which represents something else. Operator, so to say. I guess that will be important for the second part, but I have no idea what the second part is. Basically, a literal value package, type ID 4 package, is something like that. We have 3 bits, VVV, which are the version number. So that's 110 and that is 6. Next we have the type ID, which is 4, which means that this is a literal package. And next we have something. The next 3 bits after that this is a literal value. Yep. So for a literal value we have this scenario. So after that we have groups of 5 bits. And each of group of 5 bits tells us whether it's the last group. We have the 5A bits have a leading one, and that means this is not the last literal value. And the value itself is the rest of it, 0, 1, 1, 1. Next we find 1, 1, 1, 1, 1, 0. So this is not the last group, and we have this. And so on and so forth until we get to the C's, and after we get to the C's start with 0, so that is the last one. Everything after the last one we are basically ignoring. So we're gonna have to build some kind of a parser for this. So let's start, so to say. And I will actually use the test method that I'm doing here. Only our input, I have no idea what our input will be, but we will have to use the test method where we can actually test some things. So I will be creating a method that says parse packet, and that gets an input that's a string, let's say, and returns something that I have no idea what it is. And our input, and we will need to test this using parse packet, and this will be our entry. So that means that our input will most likely be a string. Yeah, why not? A string. and this should return a string. Yeah. So let's see how we are parsing this packet. So first of all, we will need to transform this thing into a binary string and into a binary number. We can always use parseInt, and you may have noticed that I always put a 10 at the end. Well, now I will actually put a 16 at the end, and this means parse this integer assuming that the string I'm getting is actually in base 16, which is hexadecimal. And just log that. And this will be some largish number. Let's take it for a spin. This will run the test method actually. Yeah, I'm getting some largish number. And if I put this into not a scientific, I want to see the programmer, so I'm working in decimal. And this is let's see, this and this should be the same. Yeah, so that conversion went well, but I will do some other magic. I don't think that I want to be using JavaScript to twiddle bits, especially as we have grouping of 3 bits and 5 bits, which are kinda hard and will go through byte boundaries, because you can see that here we have them nicely grouped in 4 bit boundaries, and so this is 1 byte, and this is another byte, and this is another byte. So now that means that I want to have this value, and then I want to have this value, and then I want to have this value, which crosses the byte boundary between 2 bytes. So if I have this as an array of bytes, it will be painful. So I will do a much slower and a much more wasteful thing, and I will actually treat this as a string. And I will use one awesome option of JavaScript, and that is, if we are calling to string on a number, we can say the base that we want returned. So if I'm not mistaken, this will return me a string with the binary representation. So you can see that this is white, this is not yellow or any other color, this is a string. And with this string I can do stupid things like taking out the first 3. Now I can have this, and now I can say const, well, the first 3 bits are the packet version, so that the version is in binary dot slice starting from 0 3 things. Const type is binary dot slice starting from 3 ending with 6. Yeah, give me the 3rd one, the 4th one, and the 5th one. Don't give me the 6th one. Give me the version and the type. And this will be strings. One 10, 100. 110, 100. That is correct. And I actually can give this to parseInt and parse it from binary to a number. Yeah, 2. and this should give me 6 and 4. Yep. So now starting from the 6th position, and to be honest, parsing usually requires us to use these parsing binary formats will require us to use these kind of constants, because we have some kind of a layout in memory, and that memory is set up so that this bit means this bit means that. So I will hard code a lot of magic numbers, and they are basically taken from the specification, so to say. So we're starting from the 6th, and then we are taking a value, and I guess we can assume that we have at least one literal value. If we don't, we're gonna break something. So we're getting the literal, so we won't slice for, oh no, this is wrong. So we need to get the literal, and the literal is actually start with start, end with start plus 1. So just get 1 thingy, and we need to ask, is this equal to 1? Actually, is this equal to 0? Yeah. If it's equal to 0, then this is the last one. And the value itself, yeah, we can do that, but start with at start plus 1, at end at start plus, so we're getting 6, then we have 7, 8, 9, 10, we need to go up to 11. Start at 6, but start plus 1, and go to start plus 5, and we're gonna say literals is an array of numbers, and we're gonna push it to the literal array. Again, we're gonna just say if this was the last one, break. Otherwise, increase start by 5. The only thing is that start cannot really be a constant. Let's see what we get. If I am correct, we should get 6, 4, and let's not see, which should, the number we should get 7, and this is 14, and this is 5. 7, 14, 5. Maybe we could have left these as strings, but okay, we'll see. Let's assume that we need them as numbers. And this is one format. So now what I will do, I will actually declare this as a type. And the type will be 4, and it will have a version that is a number, and it will have literals, which is an array of numbers. And I will have another it's not package, it's packet. I have a problem because in the language that I'm usually speaking, my mother tongue, Macedonian, package and packet is actually the same spore, and it's called packet. So type will actually be a number, And this is a thing that I honestly have no idea how to do in TypeScript, to make a type annotation that this can be any number except 4. So I'll just leave it as a number. Do we have an exclude? There are some partial types. I think that we can do this. Yeah, this will work. And this also has a version which is a number. And this has, let's see what everything else has. And then we're gonna declare a type, which is actually a union type of this. We also mentioned that the type packet is actually either a literal packet or an other kind of packet. So parse packet will always return a packet, and we're not returning anything, so we can just say return type version literals. And this doesn't know that our type is 4. Let's return 4 right now. This will work. And this is the magic of TypeScript, because since type in the packet type, what will in the type called packet, what will be the value of the property called type? It will be any number. So it knows if I just say that type is of type number, as it was inferred here, that means that I can specify the type, I can specify the version, because those exist across the board. There is a property called type, and if it's a number, we will get to it. And the other packet, yeah, just as well. There is a property called version, and I can assign it, but is there a property called literals? We just don't know. We don't know what the version is. But I can do this, for example. I can say if type equals 4, then, and now we did a type restriction. This acts as a type guard. So if type is 4, when I'm saying return 4 here, that means that since this has to have a 4 and this cannot have a 4, that means that I have to be specifying a literal packet. So here my return value has to be a literal packet. It knows that since type is 4 and I'm making returning something that has type as 4, I have to be returning only a literal packet. I cannot return so to say other type of packet with let's say has data as unknown, for example. I cannot say that I want to return data, because it will now say, oh yeah, you want to return another packet. So that's why I'm allowed to say I'm returning literals. And here we will have unknown packet type, because for now it is an unknown packet type. But now this will return nothing, so we will not to log it to the console. And let's see if we are getting the correct type and everything. So yeah, we are getting the correct value, and we have the type, the version, and the literals. That's great. Now let's read on about the other packet. Every other type of packet represents an operator that performs some calculation on one or more subpackets contained within. So that's an operator packet. So we right now, so we did what we wanted to do with the literals, and now we're gonna do the other packet, which apparently is not anything else, is just an operator packet on one or more sub-packets contained within. An operator packet contains one or more packets. Okay, we know how to manage that. That means that we can have sub-packets, which is an array of packet. Because those sub-packets, I think that can be other operator packets or can be other literal packets. So we can have a hierarchy. We can have an operator packet that contains two operator packets, that each of them contains 5 literal packets. Or 4 literal packets and an operator packet which contains another literal packet. All of that is allowed. So this is a deeply recursive definition, because operator packet includes the packet type and packet includes the operator packet type, but this is just how you model your whatever you have. And I will also add this now. If type is 4, actually the parsing is different. So this is the parsing that we need to do for literal packets, and then we just return that. And here we will do the parsing for the non-literal packets, for the operator packets. And let's see what an operator packet is. Just a second. Oh, I made a mistake. What a mistake to make. Packets with ID type 4 represent a literal value. Literal value packets encode a single binary number. So we don't have the values (7 and 14 and 5). We have a single value. So this is not a number array, this is a string array, let's call it. So we're not parsing this, we're just adding it, and then we get all the slices, and then we need to do this. And of course we are not returning the literals, we're returning the value. Let's run this once more. We need to lump all the values that we got together. So we need to return a single value, and that value is 2021, which is basically, since we're doing 4 bits, that is 7 times 16. Let's do it. Oh, I'm in binary. 7 times 16 plus, what was it, 14 times 16 plus 5, that is 2021, which is quite a common number in these tasks. I wonder why. So we need to get a single value out of that. Okay, we dodged the bullet there. Represents an operator, aren't important. An operator packet contains one or more packets. To indicate which subsequent binary data represents its subpackets, an operator packet can use one or two modes indicate. So we have two modes, and that is the bit immediately after the packet header, the length type ID. That's this one, the 7th bit. So let's take the 7th bit. So we need to parse this now. This is the value that we want to do. And this should blow up right now with the error that we removed the error, so we return nothing undefined. Okay, so we need to get the length type. The length type. Is 0 that the next 15 bits are a number that represents the total length in bits of the sub-packets contained in the packets. Length type ID. That's actually, I'm gonna move this as well here, because this is kind of a constant from 6 to 7. Take it, and now we can do, if this equals to 0, then we are doing total length parsing. Otherwise we're doing number of sub packet parsing. And let's see if we have that. Done correctly. And I guess there was an example with the length type ID. So if we are correct, we should see both options present. Packet 2, packet 1. Yep, and undefined, of course. So we got this far. How do we parse it? The 3 bits are the packet version. Packet type ID 6. The bit labeled I is the length type ID. The 15 contains the length of the sub-packet in bits. 15 bits labeled L. So we need to take 15 bits, and those bits are from 7, 7 and 15, 22. And of course we're gonna parse in this. from binary. Let's see what is the total length. It should be 27. It's 111, which is something that is quite different. Looks okay. One, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Let's see. So we have three numbers for the version, three numbers for the variant, one more for that, and let's put a dot here and a dot here. So we should have taken starting here, and it seems we took starting here. What am I not counting? And that is exactly what I started with. Let's put a breakpoint. This is definitely not a binary. Let's see what happens. So our hexadecimal should be something like 38 and so on. Yes, 38. And the binary is something that starts with some zeros. This doesn't look too much like what I wanted it. We're missing two zeros at the beginning. Oh, shit. We need to, yeah. We need to have leading zeros, because this one didn't have leading zeros. This one, we need to basically, right now, this number that we are starting with, this is the correct value. the other hand, this is 63. Yeah, we'll need to basically do this character by character. Yeah, for example, if our package was just D, that would turn out to be, well, D is, let's call it A because A is actually 10. That will be 1, 8, 0, 1, 0. That is 10. And if our package was 3, that would have been 11. And that's what we got. And actually we wanted this to be 0, 0, 11. So we need to transform each of the numbers separately and add leading zeros as necessary. And the other thing is, if we have something like this, this will transform into something that is bigger than 64 bits, so we might lose precision. And as you can see, that our input is quite large. So since we're working with strings and strings are not limited by anything, we can just change the parsing a bit. So we're not just changing it to anything, we will just say input.map.split actually on each space, and then map each character to parse it as a 16 base number, and that will give us 1010 for A, it will give us 11 for 3. I'm gonna say, actually that's gonna give us 10 for A and 3 for 3. I'm gonna say to string of 2, and then I'm gonna add something else. I'm gonna pad at the start, so to the full length of 4 with the character 0. And then I'm gonna join everything together. So this is useful but not too useful. Actually, let's start it now. Yep, we got our total pack size, which is 27. So what do we do now? It's 27. We're up to here. So we have some more packages. How do we determine what is the next package? Well, yeah, we can start parsing the next package. How do we determine when the packages are finishing? Because this might be a package that is linear, that is literal, or it can be another operator package. On the other hand, if I take all of this and turn it back into a hexa string, actually I will create another method. And I will create another 2 hex string. Actually, let's not be fancy, let's use this. We need to return a binary string to a hex string. Well, this isn't gonna cut it because we know that 16 is bigger than 2, but 2 is not bigger than 16. So we will actually need to kind of chunk it out. We cannot just split the binary string on each thing. We need to split it on fours, so to say. Start is less than the binary string length. Something along these lines. The hex letter is sliced from the start to 2 and then add 4. Only this won't return the correct result. We can always do right now hex is a letter and we can have something like hex digits and just has hex digits dot push this and result is hex digits dot join. Let's see if these are working. Oh, I will just say const binary equals to binary string of input. Now everybody is happy, but I don't want to test this. I want to test this to hex string, to binary string. Let's see what happens from A, and let's see what happens with 3A, and let's see what happens to A3. Yep, we are getting good strings, so this seems okay. Let's see to hex string of this, and similarly to hex string of this and of this, and I have a feeling that at least one of them will be wrong. A, 3A, A3. That's okay, but what happens if I try to get a hex string of this, and this is also A3? As with normal numbers and the hexadecimal numbers are the same, so the leading zeros do not count. But I think that we might have a problem with that. We got E2. But actually in our case, leading zeros are on the other side. So A2 is actually what we wanted to get. No, 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 no. If this is not a multiple of 4, we actually needed to get this. We needed to get E8 from this string. Because we're not adding padding to the left side, we're adding padding to the right side. And to hex string, this is not the valid. I will add this method because maybe a few years down the road I will find this method that actually parses it incorrectly, because we don't need to pad it from the left, we need to pad it from the right. And we might have a problem with that. So we're gonna slice this into 4 letters, but we're gonna pad at the end up to a length of 4 with zeros. Yep, got an E8. So why am I doing all this? Because now I can basically just, I got the total length, so I know that the total length will be 20, needs to be 27, and I can take those 27 and I know that it starts at 22 and it goes up to 22 plus local length, and I can say parse packet of subpackets data, and I will just transform it to a hex string. And just console.log the subpacket, because I will get a single subpacket, and let's see what we get. We got nothing because we didn't call the method. We got something that is type 4 version 6 and the value inside is 10. The 11 bits labeled A contain the first subpacket, a literal value representing the number 10. And now I have a problem because I cannot know where the second subpacket starts. In order to know that, I will literally have to find out where the packet A ends. And I will have to know that either way, so I will add something like this. I will actually do this. The base packet interface that will have the version, and it will actually have a type that is a number, and it will have the length, which is also a number, and I can extend base packet, and I can extend base packet, and then I don't need this. I still need the types because I'm actually restricting that. And you can see that base packet is only used to be actually interfaced from. I can actually just call this I base packet, but that's not something we do here, so let's do that. So this means that I get to return the total length in bits that I actually used. So for If it's the last, we're again gonna increase the length, and this length this times is, well, yeah, we can do this as well. Now, where were we? So, we need to test whether we are calculating the length correctly. Let's go back to our original example as well. That's this one. Let's just do this. Console log of parse packet of this. And this as well. So the first one says that we had a length of 21 characters, and let's just see. Three, four, five, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, and then we had 3 zeros at the end that we're not actually using. So our length is correct. This is indeed long, 21 characters long. So we have enough information in order to construct this subpacket. So we have all our subpackets in a row. Well, now it's about 2 hours later. I have no idea where I stopped. So we'll just continue from where we started, and I think that we managed to have our subpacket parsed, and this is a packet, and then we can get that subpacket subpacket's length. So we have the total length, and we can have a processed length. That's how much data we processed so far. So far we processed 0 bits. Then we get the subpacket data, we process that subpacket data, and we know exactly how many bits we processed. So we can say that the processed length, we're going to increase the subprocess length by the length of the subpacket. And then, of course, we can slice that off the subpackets data. So we can say, well, process length is different from the total length, and that assumes that the total length is actually a correct number, otherwise we're just gonna continue running. We need this here. We get a subpacket, we increase the process length, and then we slice that much off the subpacket data. So the subpacket data gets thinner and thinner and thinner as we go, shorter and shorter as we are taking subpackets and processing them. And of course we will gonna need the subpackets, and for each subpacket we're gonna need to add it to the subpackets array. Let's do that. We don't need this, we need this. Let's see if this works. if we are correct, we should get an array of 2 subpackets, which are basically literal subpackets. That's okay. And one has a version and with a value of 10 and with a value of 20. And let's see what we needed to get. The 11 bits contain 10, the 16 bits contain 20. The 11 bits contain 10, the 16 bits contain 20, and then we are done. So yeah, this means that we are kinda okay parsing the length, the operator packet length type ID 0. Now we need to do another processing for operator packet length type ID 1. Oh, just a second. If this is, we need to actually return our thing. And we need the type, we have the version, and we have subpackets, and we need to return something about like that. This is the total length plus 22. Yeah, because we sliced off 22. So we have the third thing that we need to parse, and the third thing is this. So far that will just, let's see what we get. Where do we have a console log? Outside of the places where we actually want to have it. We have it here. Okay. Yeah, so I was hunting for this one. So we have the literal, the operator 0 that has 2 subpackets that were literal inside of it, and now we need to do the number, the subpacket number parsing. So we are getting here. And how do we do that? The 11 bits labeled L. So we have 11 bits. This is a coincidence. Yeah, which indicates that the length is an 11-bit number representing the number of subpackets. So yeah, we need to get the total number or subpacket number. Let's just call that sub number. And we need to take 7 and 11, that's 18. Okay, and then we need to parse everything else. We're gonna need to that we're gonna need subpacket data, and that's gonna be something like this: binary dot slice 18. And we're just taking out 18 thingies, and that's about it. So instead of the length, now we're gonna have to have a count. So while the count is less than the sub number, otherwise the logic will be somewhat the same. And we're gonna need to process length as well, because we wanna return our own length. But now we have the process length. So we're gonna need to get the subpacket data, convert it to a hex string, and parse it out. And we were gonna get a subpacket. We're gonna parse that subpacket. We're gonna increase the length. We're gonna remove that thing from the subpacket data, and then we're gonna need to increase the count. And we're just gonna loop until we're done. So we're gonna return the type, the version, the subpackets, and the length is the length of all our subpackets plus 18. So the length is kinda cumulative. Let's see if this might work. So we have 3 different cases, and those are 3 cases. So we have literal, operator 0, operator 1. So we have type that is a 3, so we have version that is a 7, and we have 4 literal subpackets, each of length 11, with values 1, 2, and 3, and the length. Okay, and now we need to parse the hierarchy of the packets throughout the transmission and add up all of the version numbers. Okay, and we know that we have a single packet. So that single packet might have multiple packets, might have multiple packets, and so on and so forth. So what we're gonna do in our we don't need you, we will hide you, we will hide you. So we have part 1. We need to do something like const packet equals parse packet of input. And we didn't run the process input task as well, and that will be read input, and this is a string, and return the input unchanged. So processing the input is kind of simple. We have that input, we're gonna parse the packet, and we're gonna have to do something like this: const get total version sum of a packet that's not an operator packet, that's a packet, because parse packet will return a packet. Yes, this is what we want. And now my type inference doesn't really work because of that, but it should work now. Length type version. Now I want value. This is 4, and this is anything but 4. Well, we can always cast it. So this is a simple and recursive function. So if the packet is a literal packet, actually, why do we need to cast anything? We kinda do, but for the other case. We return the version actually. So if it's a literal packet, we have that, otherwise, no, the type inference is kind of faulty. Otherwise, so if we don't have sub packets, we return our version. If we do have sub packets, we return our version plus the sum of our sub packets get version. And I'm gonna write this in the long way. So map it and then run a sum. This is a custom method that I'm using that just reduces as it should. So return get version sum of packet. Yeah, so it's that simple. We'll just parse the packet and then get the version sum. Yeah, that's as simple as can be. Only parsing the packet could be a bit complicated. So we have a few test cases that we need to run through. That's an operator packet that contains an operator packet which contains an operator packet which contains a literal value with a value of, oh, we didn't run test, we needed debug. So with a value of 16. Yep, that's 16. So this is an operator packet which contains two sub-packets. Each sub-packet is an operator packet which contains two literal values. Let's see if that works. It finished and the result is 12. This has the same structure, but it's with a different length type. So that is 23. This is an operator packet that contains an operator packet that contains an operator packet that contains 5 literal values. 31 sum. So it seems that it works for all of my cases, so I will test it with my real input and we'll be able to see if this thing actually works for our real case, because we don't want our examples to run, we want our real case to run. So the sum of our whatever of the versions is 960 and the moment of truth, it's the right answer, 1 gold star closer. And now let's see. We have a bit more to read. Now that you have the structure of your transmission decoded, you can calculate the value of the expression. Okay. Literal values represent a single number as described above. Okay. Let's see what the other type ID is. Packets with type ID 0 are sum packets. Their value is the sum of the values of their subpackets. Now I have an idea where this is going, so I'm gonna do this. We're gonna have a method that takes a packet and evaluates it. And Mm, yeah, we're gonna need this because I have no idea why, but this returns. Um, we're gonna cast it so that it works, and now we set if it's a 0 packet, then the value is the sum of the values of their subpacket. Okay, so we're gonna have the subpackets and evaluate them and return their sum. Else, actually we don't need an else, we have a return. If it's 1, as they say, that's a product packet. We need to multiply everything together, and so we need the values. Actually, I think that we're gonna need the values in any case. So if it's a 0, we have a sum packet and return the sum. If it's 1, we have a product packet, so we return values dot do I have a product method? No, I don't. This just assumed that I might have it. We're gonna reduce, and for each a and b, return a times b and start with 1. An error would be to start with 0 because that would give us a 0 all the time. So we're gonna start our accumulator with 0, and then we're multiplying it 1 times 3 times 5 times so on. So packets with ID type 2 are minimum packets. Oh, it gets this, and 3 is of course max packets, and of course I have the min and max functions. I didn't manage to need a product function because that's not something that is usually needed. Packets with ID type 5 are greater than packets. Oh, this is getting to be programmy, so to say. Because we using the packets, we can do some evaluation. Their value is 1 if the value of the first subpacket is greater than. So the next 3 ones are the logical packets. I will call these arithmetic packets, and the next 3 are the logical packets. Yeah, it assumed that the logical will be the end, but it's not. It's actually greater than. Than packet. And for the logical packets, we will always need const first, which is values of 0 and second. And let's see, their value is 1 or 0. First is bigger than second. We're just gonna do this. First bigger than second, return 1, otherwise return 0. And of course 6, 7, less than and equal to. So it's gonna be this, and it's gonna be this. You can now work out the value of the outermost package. So let's see this. Because the code of part 2 will be this. We're just gonna parse it and then we're gonna evaluate it. What can be simpler? Yeah, when you say it like this, programming is just trivial, easy. But this should return 3. Exactly 3. Product of 6 and 9. Let's see if our reduce is correct. 6, product of 6 and 9, yes, that is 54. Finds the minimum of 7, 8, 9. Which is 7. Finds the maximum of 7, 10, 8, 9. Which is 9. Is 5 less than 15? Technically I don't need to check all of these, but we should. Yes, it's 1. This should return 0. Again 5 and 15. Yep. And this returns 0. Why is it larger? Yep. And this compares 1 plus 2 to 2 times 1 plus 3 to 2 times 2. And they are equal. So we need to evaluate this monstrosity. And if it just says 1, I'm gonna be mad. No, we got a quite large number. And that's the right answer. And to be honest, the second part might have been interesting to solve manually, so to say, because I'm just gonna say console log packet and see what we have inside actually. I think that at some depth it's just gonna say it's an object, it's an object, it's an array. Yeah. So we have sub-packets. We have plenty of sub-packets of various types, and most of them have sub-packets of their own. So yeah, basically we could drill down and evaluate the tree. But yeah, we can have it evaluated for us. The other questions that we're usually trying to answer is this thing fast. So let's take a look at it here. "51 milliseconds, 41 milliseconds. Not bad, not bad. Let's run all of them and see which part of the overall processing is done by this. It's something like 3% of the overall processing, so until we get rid of this one with 60% and this one with 25%, we're okay. So the total runtime is in the neighborhood of 3 seconds. I've seen that some people are targeting 1 second as the total runtime of everything, but I'm not gonna be that strict. Let's solve everything and then we can optimize however we want to see fit. Anyway, let's return to our advent calendar. This is getting to look much better. I guess we should be leaving the cave system eventually and continuing looking for Santa's sled keys. That's about all from me, and talk to you tomorrow. Bye.